about hard languages in NIZK from Unstructured Hardness.
Hi, everyone. I'm Alexis. If you had seen on the program, it might have said Amit. Unfortunately, he couldn't make it, so I'm giving the talk in place of him. But yeah, so this is joint work with Riddhi, Yuval, Eyal, Paul, and Amit. And this is our work on hard languages and NP intersect coNP and NIZK proofs from unstructured hardness. So there's a lot of words in this title. You got like NP intersect coNP, you have NIZK proofs, you have unstructured hardness. So I'm going to just break these down one at a time, starting with NP intersect coNP. Okay. So NP intersect coNP are languages for which if you have a witness, you can efficiently check whether it's in the language and if it's not in the language. So you have this sort of two-sided thing you can check. And in fact, we don't actually have that many candidate hard language in NP intersect coNP. And in general, they're pretty highly structured. So as some examples, we have factoring. We have some stochastic games conjecture, or stochastic games. We have some constructions from one-way permutations. But we don't really have much more than this, unless you're talking about the promise problem world. Oh, yeah, hard means non-NP. That's what it'll mean for the talk. But for promise problems, we do actually have a lot more hard languages. But for the focus of the talk, we'll be focusing just only on languages, not promise problems. And the reason is that the question of interest we have is actually pretty simple for promise problems and not as interesting. So it's a little unclear kind of how hard NP intersect coNP actually is. So most of the current candidates we have are broken by quantum algorithms. So factoring is, and then one-way permutations, we really only know how to build from factoring and discrete log, which are also broken by quantum algorithms. Additionally, there's some simple computational models working in Pagliazzo and Naur that shows that P equals NP intersect coNP for decision trees. And we actually don't know any complete languages for these models. And in the community, there are some people that don't really think this is hard. For example, Peter Farnock thinks that factoring is in P and therefore not hard. And then in Jack Edmund, he actually has a rock in his front yard where he's engraved that he thinks that P equals NP intersect coNP. So not everyone thinks that this class is hard. And that's kind of what we'll be exploring is how hard is this class and what can we do?
Point was actually they're different. That's why you need the fact that you have characterization for when you have matching and non-matching. That doesn't mean that you have a polynomial time algorithm. That's why you had to work so hard.
Yeah.
Maybe you thought it was a generous thing. I mean, I drive over something that says P equals NP.
Yeah. So yeah, maybe if you think it's not equal to P, you can make your own rock and stick it in a yard across the street or something like that.
That's how science should be done.
Yeah, have a little war between them. But yeah, so as I mentioned, these candidate hard languages we do have are highly structured. And one question we can ask is, can we build a hard language from sort of unstructured assumptions? So yeah.
It's probably not important, but like factoring, it's not a language, right? I mean, it's a search problem. Does it matter? Should I not care?
So yeah, it doesn't really matter for this. I mean,
but just because you made a point that you're focusing on language, right? So how should I
Factoring is equivalent to a language. You can make it into.
You can make it into a language if you want.
The conclusion is about languages. The assumption doesn't need to be about languages.
See,
yeah.
You can make a canonical form for the prime factorization and ask is the ith bit of this canonical form. Okay, so
yeah, or you could build like some crypto primitive from factoring and use that to try to build a hard language, for example. Yeah. Okay, so what do we mean by structured assumptions? So yeah, here's a quiz. Which of these do you think are unstructured assumptions? And I mean, I haven't really described what unstructured is, but you can look at these and be like, okay, maybe factoring is structured, but what about random oracles?
There's a lot of structure in random functions.
Yeah, there is some structure in random oracles, but actually for this talk, we're going to be saying that random oracles are probably one of the least structured of these. So yeah, I mean, you could argue that random oracles are still pretty structured, but they are.
Structure? Why are
So
they
structure is
structured?
unrealizable. Right?
Like, what is Adam's argument that they are structured? I don't understand.
I think it's like
Isn't there a
0,
lot of
1
structure?
laws.
What?
Pretty much any property either holds with probability 1 relative to a random oracle or probability 0 relative to a random oracle. So in this formal sense, all random oracles look alike. Is that what you're?
It's just a random function, right?
You want a machine that generates conjectured classes, you want something that looks like a random.
So, I mean, we can think of random oracles are a random function. So it, in general, won't have like linear structure, for example, like LWE or like strong algebraic structure. And I mean, random objects are kind of as close as we can sort of get to unstructured objects. So we'll use random oracle kind of as what we define for unstructured hardness, will be ones that you can build from random oracles. And then as a consequence, we'll also allow anything that can be built from random oracles to also kind of be considered unstructured. So for example, random oracles are one-way and collision resistant. So you could kind of think of one-way functions as being an unstructured assumption, because if you just took a random function and gave you black box access, it should be one way. Yeah, so we're talking about languages relative to random. So we will define some language LO, where L is defined relative to random oracle. Yeah. And we could also say injective one-way functions could be considered unstructured hardness, because if you have a random length tripling function, then with very high probability, you won't have any collisions and therefore it will be injective. And then we have this little complexity thing, UP not contained in RP, and this is implied by injective one-way functions, so we could also consider this unstructured hardness. On the other hand, all these other things we don't know how to build heuristically from random oracles. So one-way permutations, for example, we don't know how to build that from random functions, and we can really only build it from things like factoring discrete log. So we will break it down like this and say that unstructured things are everything in the random oracle regime, and structured things are everything else. And why is this kind of a reasonable breakdown? So if we look at sort of random oracle separations for complexity classes, there's recently been a lot of really exciting work in it. So starting with the work of Bennett and Gill, they showed how to separate P, NP, and coNP by random oracles. There's another work that shows that the polynomial hierarchy is infinite relative to it. And then a very, very recent work from Fox shows that you can separate BQP and BPP relative to random oracle with respect to search problems. So there's been a lot of work, a lot of interest in the complexity community, specifically regarding oracle separations of complexity classes. And in the crypto community, part of the reason we care is that we might think that random oracle separations could potentially give us actual real world instantiations if we replace the random oracle with some hash function. So there's this hypothesis that says if you can separate them with random oracles, then you can separate them without random oracles, which has been proven to be false for IP and Q space, but it's still plausibly true for simpler complexity classes like P and NP intersect coNP. And there haven't been counterexamples for much simpler classes. And so, as I mentioned before, we can kind of, if you have the separation in the random oracle model, and you were just to replace the random oracle with a hash function, then that gives a candidate real world separation. So these are some of the reasons why we care about the random oracle model. The question then more specifically is, can we build a hard language in NP intersect coNP from random oracles? And this has been open since Bennett and Gill 40 years ago. So what's known? Again, we don't know the separation. And in fact, there's another work by Tardos that shows some difficulties if you try to do the separation. And if you're just trying to use basic crypto, then we actually have some possibility results from black box constructions. So you can't build it just from one-way functions. And even if you assume IO, which is extremely powerful, there's also no black box instructions from injective one-way functions in IO. And this rules out a whole bunch of crypto because you can use IO and one-way functions to build quite a lot of crypto. Yeah, that's what we have so far. And what our work does is the following.
So does that extend to like a black box separation for random oracles, saying that you cannot have like a black box, a line, or?
Yeah, so this construction does not deal with the random oracle model. It just says, suppose you were trying to build a language in NP intersect coNP, but not NP, assuming only, let's say, injective one-way functions IO, then you can't do that if you use a black box construction of from injective one-way functions IO. Yes.
I just want to mention that you don't actually get this result from either my work with Manuel or Stephen Riddish's work alone. You need the results several years later of Constock.
So I will add this reference.
Constock and Smith. Smith with a Y.
Thanks for that. I will add the reference.
If I build a commitment scheme from a random oracle, and does it give a language in NP intersect coNP? Language is a commitment transcript plus claim of
Wait, so you have, so you IO, wait, so you,
I don't use IO.
so you build a
commitment
commitment scheme.
a transcript plus a bit, let's say 1. Actually, the commitment, when the commitment is really a commitment to 1, it's in the language. If it's not, if it's commitment to 0, then it's not in the language. Your certificate will be the decommitment information.
Like perfect binding languages.
Yeah, so here we're dealing with NP intersect coNP, which is not randomized. So you would want it to be like perfectly binding and perfectly hiding for that to work. Yeah. But yeah, if it was maybe like, you know, some probabilistic version, then that might work. Yeah.
So promise problem is return back to 1 to 0.
So yeah, so actually for promise problems, you can build it from just like injective one-way functions, or assuming UP is not equal to P. Yeah, I mentioned earlier, but promise problems, this is actually fairly easy to build. Something that's in NP intersect coNP, or promise NP intersect coNP, but not promise. So our main theorem shows that if there exists injective one-way functions, then we have an oracle separation between P and NP intersect coNP with a random oracle. And in fact, the way we kind of get around the impossibility results before is mainly because we use a non-black box use of our injective one-way functions. So, and we have
So you injective one function in the real world.
Yeah, and the previous results assumed that the P equal NP in the real world to get it to show that NP intersect coNP. So the previous result by Constock and Smith was that if P equals NP in the real world, then P to the O is NP to the O intersect coNP to the O is an infinitely often average P to the O for a random oracle. So it doesn't contradict this in any sense. So like, and if you assume that P is different from NP intersect coNP in the real, or BPP is different from NP intersect coNP in the real world, then P to the O is going to be different from NP intersect coNP by the same problem. So
so yeah, one of the nice things about our theorem is that it's actually a constructive proof. So if you were to replace the oracle with a hash function, then we actually have a polytime algorithm that can give you a candidate language that's in NP intersect coNP, but not in P. So this process basically allows you to build a whole bunch of candidate languages that might be in NP intersect coNP, but not in P. Just kind of assuming maybe that your cryptographic hash function will work kind of like a random oracle.
It's a verification process of NP and coNP.
Yeah.
Can you say anything about TFNP?
TFNP.
I'm not really sure about that.
You have hardness in NP intersect
Unique
coNP
solution
directly.
Yeah. Different problems with one solution.
With this.
NP just, NP is hard languages. Sorry, in UP, hard language in UP intersect coUP.
Which is hard. That's can be
But yeah, in fact, we don't even need injective-only functions. For us, it suffices to assume that UP, which is basically NP with a unique witness, is not continuous. So our theorem actually is this. So assuming unique polynomial or UP is not contained RP, then we have a random oracle separation between P and NP intersect coNP.
You don't get the UP intersect coNP.
No, so basically, we're using the language in UP, not in RP, to sort of replace the injective only function in our kind of construction language.
Does it have a fixed input output size, or is it for all?
Yeah, so questions about what the random oracle looks like. So here, the random oracle you can think is an infinite length bit string where every bit is completely random. However, when we use it for inputs of fixed length, we'll only ever use some fixed length of the oracle. And you could kind of think of that if you wanted as like n bits to n bits, you could always transform some finite length into that. But yeah, the technical model of the oracle is just an infinitely long bit string. So yeah, so to build this, we actually have another result, which is our main new ingredient for this is we build a NIZK proof system in the random oracle model. So here we're using only random oracles. So there's not going to be a structured random string at all. You could think of it kind of like the URS model because you could build URSs from random oracles. And note, we don't already have this from Fiat Shamir because this only gives NIZK arguments which hold for computationally bounded provers. So as our second result, we show that there exists an unbounded prover. I'll get back to that. The prover is not efficient. NIZK proof system for NP in the random oracle model. And if you just really don't like random oracles, then we actually describe some object called a delta dense pseudo-random hash function that you could build and also use to instantiate NIZK proofs. So here, assuming there exists a delta dense PRHF, where delta is just some constant that you can efficiently approximate, then we have a NIZK proof system for NP in the URS model. Before I go into a little bit more about the NIZK proofs, let me just define what this delta dense PRHF is.
What is URS again?
Oh, sorry. Yeah, URS is the uniformly random string model, which means the prover and the verifier both have access to a uniform random string. This can be contrasted with the structured random string model where the string doesn't have to be uniform. Yeah, so it's a constant and there's an algorithm that allows you to approximate like n bits of it to within like 1/2 to the n in efficient time, so polynomial time. So basically the verifier will have to use this constant. So they'll need to basically create some good enough approximation of it for every input length. So what is this pseudo-random hash function? So first it's pseudo-random, which means if h on a random input should look random, it should be indistinguishable from a random element in the codomain. We also have density, which says that if you take a random element in the codomain, it should be in the image of h with probability really close to delta. And then finally, we have this new property we call pre-image pseudo-randomness, which says that if you have two ways of taking x and y, where the first way you pick a random x and you set y equal to h of x, then this should be indistinguishable from picking first a Y from the image of H and then setting X to a random pre-image of Y. And this is kind of an element of our proof. Yeah, this is computationally indistinguishable. Yeah.
X here is sampled randomly in the domain.
Yeah, so X is a random element of the domain, U is a random element of the codomain, and Y here is a random element of the image. An inverse function just takes a random pre-image. Yeah.
How does this relate to known assumptions?
See what?
Any other known assumptions?
So yeah, I mean, it's sort of like, so we actually don't know how to construct this from standard assumptions. They are satisfied by a random oracle, but you can think of the first one as being kind of like a PRG. And then this pre-image pseudo randomness is kind of new, and the density. So I guess if you had, for example, an injective PRG that was expanding by 1 bit, that would satisfy this because the density would be 1/2. But yeah, we don't currently have any candidate constructions for it right now, but it is satisfied by a random oracle. And so we could conjecture that, your favorite hash function might be one.
Why is uniform you said about codomain? It should be over range, right?
Oh, sorry. Yeah,
Not codomain.
yeah, over the range. So yeah, so these are our 3 theorems, and let me go into a little bit more about NIZK proofs.
So is a one-way permutation, does this satisfy this or no?
A one-way permutation would satisfy it, yeah. Because the density would be 1, and then it would be pseudo-random. Well, it'd have to be, no, it had to be pseudo-random permutation. Let's see that. Yeah, so it would be, yeah, and then since there's only ever one element of the, it would satisfy pre-image pseudo-randomness because every element of the range would be equally likely and have exactly 1 pre-image.
Wait, I thought you said you don't know how you can construct it from what?
Sorry, from any unstructured standard assumptions.
So this follows from one-way permutation?
It would follow,
Yeah.
I think so, yeah, it would follow from one-way permutations.
Over like 0, 1 to the n or something, right?
Yeah, one-way permute, yeah. So, yeah, sorry about that. Yeah, we don't know how to construct it from any unstructured assumptions. You could build it from one-way permutations. You could also build it from injective PRGs if they're expanding by like k bits or something, where k is a constant. But we don't really know how to build injective PRGs, for example. Yeah, sorry for the confusion. Yes.
Function not satisfied. Do you need empty logic?
So identity doesn't satisfy this because it's not pseudo-random. Or sorry, yeah, it is pseudo-random. Sorry. It's not, yeah. So, well, we need delta actually to be less than 1 strictly. So it has to be between 0 and 1, strictly speaking, and can't be 1. So.
Is it baked into the definition that it's expanding or shrinking the number like n versus m or?
So here it's kind of in delta. So I didn't write it here, but delta needs to be a constant strictly between 0 and 1.
Okay.
So it can't be too, it has to be expanding a little bit, but it can't be too expanding. Or I mean, I guess it doesn't have to be expanding if it has collisions.
We only would think of it in the slightly expanding case.
Yeah. So like if you went from n bits to 2n, then that definitely wouldn't satisfy that because delta wouldn't be a constant.
Pseudo-random permutation can't work because the domain and size.
It would depend. So yeah, if you didn't like, you could add stuff to the range, and if it was hidden, whether or not it was in the range. I don't know.
Okay.
But I'd have to think about it more.
Yeah.
Yeah.
So is condition 2 just that the equivalent to saying most elements have about the same number of pre-images?
If most elements have about the same number of pre-images, that implies the second one. there might be other ways, but it's just computationally hard. I guess so, yeah.
Well, is that computationally
That's
indistinguishable?
yeah, all these are computationally indistinguishable.
Okay.
Yeah. So, yeah, for example, a k-regular function where every output has the same number of pre-images satisfies pre-image pseudo randomness. And in fact, we do know how to build something that satisfies 1 in 30 from an injective PRG, but not 2. So back to NIZK proofs. So let me just explain briefly what a NIZK proof is. So the prover is trying to prove that X is in some language, or think of L as being an empty language. And here in our setting, we're doing the unbounded prover setting. So this is for the same definition as the original work of Feldman and Macaulay. And the reason, unbounded prover is not great if you want to like actually use this in the real world, but it's sufficient for our purposes here. And it would be nice in follow-up work to maybe try to make an efficient prover. And we're in the uniform random string model where P and D share a uniformly random string. And then we have 3 properties. So completeness says that if everyone's correct, or like everyone's honest, then the prover should be able to prove true things to the verifier. Soundness says that if the prover is dishonest, then they shouldn't be able to prove false things to the verifier. And here we're in the proofs, which means that the cheating prover can be unbounded as well. And then zero knowledge says roughly that the verifier shouldn't learn anything more except the X is in the language, which we can model by having a simulator that simulates the transcript that B would receive.
There's no random oracle.
Yeah, this is so this is the random oracle one. This is just the plain URS model, or just the URS model. In the random oracle model, here, rather than having a URS, you'll just have query access to a random oracle. And then zero knowledge is for verifiers that can only make polynomially many queries to the random oracle. So we'll require the simulator to also simulate the random oracle. I put this in quotes because it's kind of more like a game. You either query the oracle or the.
Allow the simulator. You don't require it, you allow the simulator.
No.
Yeah, the simulator needs to generate like queries that look like a random oracle along with what the proof should look like. And they would need to do it because they need to have their oracle they simulate correspond to kind of what the prover would have done.
The cheating prover sees the entire oracle.
The cheater prover, yeah. Cheating prover is unbounded, they can see all of the oracle. The verifier is bounded and only has bounded query access.
Typically, when we give access to a random oracle, we also give access to a p-space oracle because random oracle is hard, like with respect even to a p-space oracle. So do we do the same thing here? Then what's the notion of the computation bounded?
So here we're saying that you have, so the prover basically gets all of the oracle. They can do whatever they have, and they have as much time as they want. The verifier.
You get unbounded communication complexity with the random oracle.
Yes, the prover has unbounded access to the random oracle. Yeah, query complexity.
So computational complexity here, bounded is bounded query complexity.
Yes, the prover also has unbounded query complexity as well. Okay, so what do we have for previous work on NIZKs? So we're dealing with the yellow box, which is NIZK proofs, again, security against unbounded provers, where you have a uniform random string. Note that in the structured random string model, where the string is not uniformly random, you can get more results. But one of the things we know is that we have like one-way permutations, DLIN, all these things, but these are kind of structured hardness assumptions and not post-quantum except maybe IO. And if you want, it from like one-way functions, for example, then you have to go to the structured random string model or NIZK arguments. And the reason why lattices is down here, like why doesn't one-way functions just do everything, is because like us, they have an unbounded prover. So the lattice constructor has a bounded prover, which is nice, but we actually don't have any lattice constructions in the URS and proof-based model. So if you want unstructured hardness, again, Fiat Shamir can give you in the random oracle model, or you can go to structured random strings. But I guess that is structure by having the structured random string. In our work, we show how to basically get random oracles or NIZK proofs from either random oracles or delta dense PRHFs. And so it was previously unknown how to build this from unstructured hardness. So that's our main theorem. And I'll now go into kind of how to construct these. Any questions on the results? So first, we're going to try to separate P and NPs intersect coNP. So our ingredients here, for simplicity, I'll just talk about the injective one-way function version, although you can build it from a language in UP and not an RP. And then we'll have a NIZK proof in the random oracle model for the language, which is just the set of all y's that have a preimage. So all the y's that are in the image of F. And our language is actually pretty simple. It's the set yi pi, where y has to have a preimage x, and we require the ith bit of x to be 1. And pi should be a valid proof that y has a preimage. And if you assume this language, you would just replace x with w, where w is the unique witness that y is in RL or L double prime.
By the way, in the random oracle model for this proof, is required a completeness 1 or just over the random oracle?
That's a good question. Yeah, so what we build is we build one that has perfect completeness. It has statistical soundness, which is kind of adapted, meaning that the probability that the oracle allows for false proofs is negligible. And then we have a computational zero knowledge is what we build. So kind of assuming it's perfectly sound, which is not, so we'll go back to statistical soundness, but then you can actually show the L's and NP or to the O. And the way you do this is you can first just check if the proof pi is valid. If it's not valid, then it can't be in the language by definition. And otherwise, then there better be a single unique, there better be a preimage, right, X. And because F is injective, then this X is unique. So that X is going to be the witness, and you can check that it's the correct preimage, and then you'll just check if the ith bit is 1 or not. For coNP, you can kind of just do the same thing, except you just check if the bit is 0. So the proof kind of ensures that you definitely have this preimage X. And since there's only 1, you can just check whether the bit is 0 or 1. So to deal with statistical soundness, I won't go into it, but you can use the Borel-Cantelli lemma to deal with that. Okay. And then why is it not in P? So,
Can you just show it again? Just
sorry.
Yeah, leave it for a second.
Why is this not a promised language? Yeah. Why is this not a promised language?
What would be?
Why does every y has a preimage?
So the proof pi, if the proof pi verifies and it's perfectly sound, then it must have a preimage, because if it didn't have a preimage, then perfect soundness would say that there is no proof that would verify.
Because you can efficiently verify instances that are outside of the promise by running the verifier.
So perfect soundness would say if y does not have a preimage, then there would be no proof that would verify. And so if we know it verifies, then that guarantees by the perfect soundness of the physics that there must be exactly 1. There must be a preimage. In this case, exactly 1, because F is injective.
Yeah, so this is in some sense the core of it. Like this is scaling up the commitment thing, which works in the case of promise problems. Now we have this.
Yeah, a little bit. Yeah.
Where is the cirrus? Why you don't care about it because of perfect soundness?
Yeah, so right now we have perfect soundness. If we're dealing with statistical soundness, I guess I'll show you this slide. But essentially what you do is you say, you can prove using the Borel-Cantelli theorem and our soundness bound that with probability 1 over the random oracle, then you only have a finite number of bad oracles that allow for bad proofs. And then you can make a new NIZK proof that just removes all the bad oracles, or brute force computes the bad oracles.
So you still need to say what a cirrus is, like the URS or what's that?
Oh, the URS? There is, no, so there is no URS. We just have P and V have access to a random oracle,
The
And
random
that's it.
oracle is the URS.
Yeah, you could use a random oracle to construct a URS if you wanted, by just taking some part of the input domain and saying that output is the URS. But there is no URS separate from the random oracle.
Please repeat the for consider.
Yeah, so at a very high level, what we can prove is that based on our soundness sound, that with probability 1 over the random oracle, there exists only a finite number of oracles that admit like bad proofs that allow you to prove false things. And then we can construct a new V prime that for those finite number of bad oracles would brute force compute the answer. And then therefore.
That's basically saying that you have like perfect soundness and high probability overall. Is that what you're expecting?
Yeah, so our definition of soundness was sort of this, that except with negligible probability, the over the randomness of just the oracle, you can't have bad proofs. Yeah, if you didn't get that, it's fine, don't worry about it. But yeah, so why is it not in Q though? So if we assume that the opposite, suppose that in P of O with some probability greater than 0, then there is a theorem from Bennett and Gill which shows that there must exist some decider that basically works for all of the languages. So the statement itself would talk about a decider for each language LO. But here, this theorem allows us to kind of change the quantifier order and say that there would be a decider then that works for every L with probability 1. And if you have the decider, you can invert the one-way function. What do you do? So you have a Y, and you can just make a fake proof that Y has a preimage because you have a NIZK simulator, and then you just run D. And if pi was a real proof that Y had a preimage, then D would tell you whether Xi is 0 or 1. And because by zero knowledge, D shouldn't be able to tell whether or not you use the simulator or real proof. And so therefore D will output whether or not Xi is 0 or 1 correctly, and that will give you X in each matrix. Yeah, so basically we're just extracting X from this by using the fact that we can make fake proofs from the NIZK zero knowledge. These are our results again. And now, how do we construct NIZK proofs in the random oracle model? So our starting point will be the work of FLS, Shamir, which shows that you can build NIZK proofs for MPs from one-way permutations in the URS model. And our idea is that we're just going to try to replace the one-way permutations with a random oracle. And note that if you want to replace the URS with a random oracle, that's pretty simple to do. Okay, so how do they do it? Well, first they build NIZK proofs in what they call the hidden bits model. And then they show how to build the hidden bits model using a URS and a one-way permutation. Now, unfortunately, we weren't able to instantiate the hidden bits model with a random oracle. So instead, what we do is we build a NIZK proofs for a new model that we call the Z-tamperable hidden bits model, and then show how to instantiate that one with the random oracle. So let me just describe what this is, but first I'll describe what the hidden bits model is. So in the hidden bits model, you can think of it as you have kind of a URS, a uniformly random string, except it's hidden in some way. And by hidden, we mean that the prover gets to see all of it. So they get everything, but the verifier does not get to see any of it at the start. And then the prover can send across the proof pi and open any of the bits that they want. So here, the prover gets to see everything. The verifier gets to see only the bits that the prover chooses. And the prover, importantly, does not get to choose the bits of the hidden bit string. And then D will just accept or reject. Again, it's like the URS model, except here, the verifier only gets to see certain bits, and those bits are chosen by the prover. So suppose we wanted to instantiate this with a random oracle and a URS. I'm adding a URS onto the random oracle just to make it a little bit easier to write down, but you could build a URS using the random oracle as So one thing you might think to do is you could maybe do some inverse function, whatever that means. We'll get back to that. But you would maybe want O of xi equal to yi. And then because O is one way, there should be a hardcore bit function. You can set Ri to be the hardcore bit of xi. Why might this be nice? Well, O is hard to invert. So it should be, B only gets to see, right, the y's if we have a URS. And so therefore they shouldn't be able to learn X and also shouldn't be able to learn R. However, the prover who's unbounded can just brute force compute all the X's and then send over xi as kind of their opening to Ri. And then the verifier can just check that it's a correct opening and compute the hardcore bit. Of course, there are a couple problems. I said O inverse, but like, what if there's not a preimage? So in that case, R is just undefined. There's no preimage. Like, how do you compute hardcore bit to nothing? So in this case, we lose completeness. And you could think, okay, maybe I'll change the parameters to my scheme so that I'm compressing. So every single y always has a preimage. But actually, that's even worse because now you have multiple preimages. And if you have multiple preimages, that means R can, or the prover, the cheating prover, can pick any of these R's to use. So they have some control over what bits show up in the hidden bit string, and that ends up completely breaking soundness. So actually, if you're building this from random oracles, you're going to have at least one or both of these problems. That's just based on how the parameters work. And in FLS, they get around this by just using one-way permutations. And in fact, that's how they instantiate the model. Is they use a one-way permutation, and then neither of these problems show up. So we'll kind of need to use a different idea. So for us, we're going to set the ith bit equal to 1, dependent not on what the preimage is, but on whether or not it has a preimage. So it will look like this. So we'll set the ith bit equal to 0 if there is a preimage, and it will be 1 otherwise. Yeah.
I was actually going to ask on the previous slide, so if you already asked that, never mind. But couldn't you, like, this hidden bit model, you can do it not just from one permutation, but also from things like verifiable random functions, and verifiable PRGs, and also stuff like this. So you could try to think about these y's if you just think about them as blocks rather than just like, and just apply the random oracle in that forward direction, but not on y, but on like y comma s, where s is like something that's shown by the prover, but you use the same s for all the bits or something like this. And then the prover still has some leverage because you can like decide after the fact what this s is, but you can sort of amplify the hardness so that like the space of the s's does not allow you to actually sort of change things are done in like NIZK based. Is it something that you were?
We haven't really thought about that sort of approach, but there might be.
You build them from NIZK, right? So.
And no, but okay, but this is around. I'm not saying constructive URF. I'm saying sort of try this approach with a random oracle. Okay, but never mind. I guess.
Yeah, maybe we can talk about it afterwards. Sure. So this will be our new scheme, and why might we be secured? Well, for a random oracle, you can't really easily determine if there's a preimage. The best you can do is just like try to guess what the preimage is and then check if it's correct. And what the prover can do is they can, if there is a preimage, they can compute it and send it over to the verifier who can check. And if there's not a preimage, they're just going to say has no preimage. Now, this should immediately bring red flags because the prover can lie about that. I mean, if there is a preimage, they're like, oh no, there's no preimage. I lied. So, yeah.
But roughly how many are going to have no preimage.
Yeah, that's correct.
And that's how you're going to catch them.
Yeah. So we will be using some statistical tests. Yeah. So spoilers, that's what we'll be doing in the future is using some statistical tests to bound how many times they can lie. Yeah. So, yeah. So our solution for this is just to define a new model that lets you lie in this one-sided case. What?
How do you achieve perfect completeness? Because it's more probability.
Yeah. So the perfect completeness, we will also amplify.
Because some probability there's really few preimges. Then you reject the first.
No, but then you just have zeros, right? It just tells you whether the hidden bits are 0 or 1. So maybe the entire hidden bit string is 0.
Then verify. I mean,
That's true. I
I
think.
want to check there's enough claims, item to claim.
I think,
Yeah.
let's remove those.
I think we also use the Borelli-Campelli model for that.
So do some global fixing, basically.
Yeah, so I believe actually was like a very high probability
Oh,
completeness, yeah. But yeah, I think what we did was we first, we did the transformation when we built this proof and then did the transformation for that later for the soundness. Yeah, we did do that in 2 steps. So the Z-tamperable hidden bits model is just the same as the hidden bits model, except the prover can lie when the hidden bit is 0. So if it's 0, they can lie about it and say it's 1, and B will receive either 1 or 0 of their choice. And we call it Z-tamperable because this looks kind of like a Z channel from information theory. And this really captures the ability that the prover can lie by saying there's no preimage when there actually is one. But the honest prover is never going to lie. They'll just open them to the correct bits. So as you know, as pointed out, P actually can't lie as much as they want because if they lied and said everything's a 1, the verifier would be like that. That seems unlikely, so I'm going to reject. So, yep, yeah. 1 and 0. Uh-oh. Okay.
So maybe
Yeah. Okay. So, okay. Sorry about that. Yeah, so we're going to add some statistical tests. And what we can show is that if you assume that the hidden bit string is actually a structure, if it's a cycle graph, then I'll skip through this. But in fact, this also works in the Z-tamperable hidden bits model. So if you assume a structured hidden bit string, then actually it still works because flipping 0s to 1 is not going to help you. On the other hand, if R is on the cycle, like what do you do about that? So what FLS did was they used a clever way of sampling graphs so that you got one that's a cycle graph with high probability. So there's a protocol. And basically there will be these good matrices and these bad matrices. And you want to have at least one good matrix, and then the proof will work. But a cheating prover can turn good matrices to bad ones by adding 1s and invalidating them. And they can also turn bad matrices into good ones by pretending they were actually good ones. And so we sort of need to constrain how many good matrices can become bad matrices. Sorry, I'm skipping so much. But the way we do that is you'll kind of check basically for like how many 1s are in the matrix. And basically any good matrix that becomes bad will have to have at least n plus 1 1s, but there aren't enough bad matrices you can swap that. But I can go into this more in detail afterwards if you're interested. Okay, great. So yeah, so what we do is we increase sparsity matrices and we add statistical checks. So these are main results and a couple of some questions. And unconditional oracle separation would be great. Efficient prover would also be great. And then if we could instantiate this from, I guess, standard unstructured assumptions, the delta dense PRHF, that would be great as well. Thanks.
Speaker who's online saying